Okay, so in this video, we're going to take a look at intermolecular forces. I know you saw them a little bit last year in your IGCSEs, but basically when we're talking about intermolecular forces, we're talking about those forces of attraction that occur between molecules. That should not be confused with intramolecular forces, which are the forces that bind elements together inside of a molecule. Individually, when we're talking about intermolecular forces, they're weaker than intramolecular forces, but together they can dictate how molecules act. Now, there's three intermolecular force categories that you need to know from strongest to weakest. These are hydrogen bonding, dipole-dipole forces, and London dispersion forces, not named after the city and named after someone whose last name was London. Sometimes I'll use LDF just because it's a lot to write London dispersion forces. Now, London dispersion forces and dipole-dipole are collectively known as van der Waal forces. So if you ever see that term, you know we're either talking about dipole-dipole or London dispersion forces. Now let's take a look specifically at what kind of molecules have these forces. When we're talking about London dispersion forces, it includes all molecules. When we're talking about hydrogen bonding, we're talking about things that have hydrogen that is bonded to nitrogen, oxygen, and fluorine. And then finally, when we have dipole-dipole forces, we have molecules that have a dipole or are polar. So they're things that have a dipole basically have a positive and partially negative place. And so these are polar molecules. And again, all of these forces arise because of some sort of electrostatic attraction. What differs between each of them is what the electrostatic attraction is between. Taking a look specifically at LDF, when we're talking about the electrostatic attraction, we're basically talking about the attraction between an instantaneous dipole, so something that instantaneously has a positive and negative charge, causing an induced dipole. Now, that's a lot of new words, so let's just take a look at how that happens. So if we take a look on average at the electrons in a molecule, we would see basically electrons spending an equal amount of time around each nuclei in the molecule. However, at a specific point in time, at a specific instant, just because of random chance, the electrons would actually be spending more time around one nucleus in the molecule than the other, causing that end of the nucleus to be partially negative and the other end to be partially positive, just randomly because the electron cloud distorts. And wherever there's more electron density, that would be considered that partially negative charge. This creates a dipole, aka something with a positive and negative charge. And what ends up happening is that instantaneous dipole, that dipole that was created just randomly in an instant, is not alone. It's surrounded by other similar molecules, and what happens is that partially positive and partially negative distorted electron charge causes a distortion in the neighboring molecule. So the partially negative, the more electron dense, repels the electrons in the other molecule, and what you end up with is an induced. It's a dipole that has been induced by the first dipole, causing a chain reaction of induced dipoles where one side of the molecule just randomly by chance had a negative, partially negative charge due to the electron density distortion. That causes a chain reaction and we sort of get that negative and positive end. Okay, so now let's take a look at what are the effects of the London dispersion forces on boiling point, solubility, and conductivity. Well, first of all, the main thing that really affects the effect of London dispersion forces is the mass of something. So the greater the mass of a molecule, the greater the electrons. And the greater the electrons, the stronger that instantaneous and induced dipole is. If you have 3 electrons in that cloud, it's not going to be as strong as having, say, 1,000 electrons in that cloud. That just magnet is going to be stronger. And so a larger mass with more electrons will have a higher boiling point and melting point, due to London dispersion forces. So if we take a look at these three structures that I've drawn, I've only drawn the carbon backbone, so there's no other elements. It should be all hydrogen around each of those carbons. The smallest one is a gas, the medium one is a liquid, and then if we multiply all of that by about 2,000, we get a solid, which is plastic. And so here you can see our boiling point is increasing as our mass increases. Similarly, in terms of aqueous solubility, mass is an important factor. However, in this case, the greater the mass, the lower the solubility in water. So the lower the aqueous solubility. If we take a look at these two molecules, which are exactly the same, except for one having more carbons, the one with only 3 carbons is soluble in water, and the one with more is insoluble. So again, the greater the mass, the lower the aqueous solubility.